I'm Jack Dongarra. I work at the University of Tennessee, Oak Ridge National Laboratory, and Manchester University. So I have quite a number of places that I affiliate with. And my area of interests lie with mathematical software. So we've been involved in the development and adaptation of mathematical software, in particular numerical libraries, for many years, for probably better part of 25 or 30 years. Our software is open source. We were probably one of the first to have open source software. Much of the software that's developed for these numerical libraries is written in Fortran and also in C. We usually have a binding in C and in Fortran for any kind of package that's created. It allows for easy use within the environments that most people in scientific computing could easily address and use. We were involved in the creation of the BLAs. So these basic linear algebra subprograms came out of a small group of people who developed the concepts, who exposed it to the community, and who ultimately developed that pseudo-standard. That was one of our foundations for the numerical libraries that we create. And then on top of that are the libraries that we have in linear algebra, in particular in solving systems of linear equations and also in eigenvalue problems. So those are the libraries that are created. They're built on top of software layers that have the BLAs at their core. So when we moved to the GPU, to a hybrid environment, it was quite natural for us to take that software and to move it to CUDA. So CUDA has a set of BLAs. It was easy to plug it in and to use it. So the transition to that environment was really quite simple. And we still had to adjust some things, so I don't want to make it sound like it took no effort at all. But that movement from the existing base of software to the CUDA environment and to running on the GPU itself was really quite a smooth transition. It allowed for considerable performance increase and allowed us to get our first initiation on the machines from NVIDIA and from others to experiment with. This area of hybrid computing I see is really the way for the future. I see that machines that we use down the line will be made up of commodity processors with specialized processor capability. Today we have a situation where they're quite separate in the sense that the commodity processor communicates over a relatively slow link to the graphical processor in this case. But I see over time the integration of those two things to be very tightly coupled and allow for very easy and very fast movement of data. One of the things that struck us with using these devices is the fact that single and double precision have quite a performance spread. That is, in certain cases, it could be a factor of 5 or even 10 in performance using single over double precision. Now, most of the scientific calculations exist in double precision. So we don't want to give up the accuracy that we have with double precision. So it led us down a path of looking at algorithms or potential algorithms that would exploit single precision computations for the bulk of the computation and then use the double precision to refine the solution. So we have some very interesting and I think very topical algorithms and software today which do most of the computation in single precision, extracting as much performance as they can, getting an accurate answer in that precision, and then using double precision to refine the solution up to the point where we would have gotten had we done the whole computation in double precision. So we can show some rather classic algorithms which can be expressed this way, and the performance impact is quite dramatic. So we basically run at the speed of single precision. We do the bulk of the computations, order and cubed operations in single precision, and then switch to double precision for the refinement of the solution. And that refinement requires only order n squared operations. So we really are getting the benefit of the performance of single precision, yet the algorithms have the ability to capture a full 64-bit accuracy. So I see things going in the future along these lines. That is to say, hybrid architectures will be something that's here with us for many years. And the fact that single and double have a disparity has been something that actually escaped our eyes, escaped my mind for a long time. Even on our commodity processors, on our Intel or AMD processors, there's a factor of 2 between single and double precision. So if we can exploit that, it'll be beneficial even in that environment. But clearly with attached processors, GPUs in this context, there's a big improvement that one can see along these lines. And I think that's an interesting avenue for research. It allows us to experiment with new algorithms, trying to exploit that architectural feature.